Hello everyone. My name is Jialun Liu, first year PhD student working in Sheffield Biomedical Robotics Lab and Sheffield Micro Robotics Lab at the University of Sheffield. So here I would like to share some of the works in our lab related to self-folding origami robots. So when it comes to manufacturing problems, we may want to ask one question, which is how to create a 3D structure effectively. Well, the use of the origami, the traditional arts of paper folding, allows us to manually fold up a 2D paper sheets from a 3D desired 3D structure. Has been proven to be an effective method of rapid fabrication of the miniature robots. So as for the structure of a material is the most important feature in defining its functionality. So the ability of the robot that can reconfigure their shapes autonomously may allow the robot to have more functionalities. So here we want to present self-folding origami, which is the ability of a 2D structure that can fold automatically, then change its shape, then allow the robot to have more functionalities. So here we would like to show some of our previous studies of self-folding origami. So the first video shows a small self-folding origami that can autonomously fold itself to a predetermined shape. For example, here is a turtle. So when it's receiving heat from a hot air gun, the sheets can fold themselves. Then while the second video shows it is also possible for us to fold a curved creases. If you have experience on origami folding, you may find it is quite hard to fold curved creases. But here we are able to fold up, to let the sheets fold up themselves and fold to a very beautiful propeller. Then the videos on the right-hand side shows one of our medical applications of the origami robot. So the robot, it's an ingestible origami robot that can be encapsulated into an ice capsule. So the origami structure itself is made of several biocompatible materials and biodegradable materials. So when a patient who accidentally ingested one button battery swallowed the ice capsule can be navigated to the position of the button battery, then dislocated it. Then after that, the ice melts, then the origami folds up. Then we are able to move the origami robot to the wound, then pass the wound and deliver a drug. So in our case, we are using thermal responsive shape membrane polymers to trigger the self-folding behavior. So the SMP shrinks at a certain temperature. For example, in our case, we use PVC, which shrinks at around 65 degrees Celsius. So basically, the self-folding sheets has a structure of a temperature-sensitive SMP shrinking sheet with a contraction layer, then sandwiched by two non-shrinking rigid sheets, say structure layers. So when heated, the contraction layer shrinks, then the rigid structure layers restrict the contraction of the shrinking sheets. So then the varied gaps on the top surface and the bottom surface will induce a difference of shared forces. So this shrinking polymer then will create a torque along the origami hinge to fold up the hinge, resulting in a certain folding angle, while the folding angle itself depending on our geographical design, which is a crease design. Then as for the fabrication of the self-folding sheets, so first we will design a crease pattern. Then with the designed crease pattern itself can be etched onto the structural and adhesive layers with a laser cutter. Then we stripped the unnecessary components from the pattern. Then from the structure layer itself, then placed shrinking sheets. Here is PVC. in between the front and the back forms of the crease pattern. Then finally, we press these two sheets together, then remove the supporting layer. Then we are able to get one self-folding sheet. So here is our proposed origami crease design pattern. So the figure shows a view of the crease pattern design from the top and from the bottom. So it also shows the two photos. One photo is unfolded 2D structure and folded 3D structure. So when the shrinking layer received heat from a heating pad on the work surface, the origami's crease pattern will bend along the middle of the gaps, then form a robot shape. So the robot itself is equipped with a cube magnet, which allow it to be controlled by external applied magnetic fields, and the receiver coil and the capacitor used to wireless powering, and two LEDs that can be able to power wirelessly by alternating magnetic fields. Then the video on the right-hand side shows the self-folding process of this robot. So here is our coil system, set up surrounding the workspace on which the robot performs. So the inclined navigation coils are inclined 45 degrees Celsius from the horizontal plane. And it's also placed at the equal distances facing the location on the workspace. So they are able to produce magnetic fields at any direction and at the center of the workspace, of course. And thus, it is able to control the locomotion of the robot equipped with a permanent magnet. Then the induction coil, however, is horizontally placed right below the workspace. You may not see it on the photo, but it is placed right below the workspace. It is able to produce a high-frequency alternating magnetic fields for wireless powering. So as for the magnetic actuation of the robot, you can see from the video below. So by applying a low-frequency oscillating magnetic fields, so the magnetic torque will transmit it to the cube magnet equipped on the origami robot, then create this kind of rocking motion. So the robot front and the back body parts are alternatively contacting the ground, and also due to the unbalanced body design and the biased friction from the legs, then it will guarantee asymmetric body dynamics, which allow the robot to move to the front. The other thing that I should say is the induction-based wireless power transmission and the control of the robot locomotion can be done simultaneously because due to the big frequency differences. So the video shows the working of the robot. The locomotion of the robot is controlled by a joystick. So we briefly test the effective distance of the wireless powering by using our current setup. So we use several accredited plates with a thicknesses of 5mm to raise the robot from the workspace. Then we find that the maximum effective range measured is around 40mm, which is approximately 5.7 times the robot height. To power two LEDs. So, and the maximum voltage then measured, transmitted is 1.5 RMS, and the maximum current is around 150 milliamps, which is quite powerful for some low power applications. So finally, we're gonna show one demo that is a robot works in a dark environment and try to work to a certain position. Then turn on the LEDs to light up the dark environment, then to show the tests hidden in the box. So the robot itself is wirelessly controlled and wirelessly powered. which will give the robot a potential to conduct some tasks in a closed or dark environment, for example, inside the human stomach. So finally, I would like to thank my colleague Xiao and my supervisor, Dr. Shuhei Miyashita, and all the members from Sheffield Microrobotics Lab and Sheffield Biomedical Robotics Lab. And thank you for your attention.